Conservation of momentum and types of collisions. Some of the most powerful concepts in science are called conservation laws. They apply to closed systems. There is no energy or matter transfer between the closed system and the environment. They enable us to solve problems without worrying about the details of the event. They only require knowledge of the initial and final states of the system. In the last unit, we learned that energy is conserved in a closed system. Like energy, momentum is a conserved property of nature. It is not created or destroyed in a closed system. In an open system, work is done to change the energy of the system. Impulse changes the momentum of an open system. The universe is a closed system. While momentum or energy can change in an open system, the momentum and energy of the universe remains constant. To apply conservation of momentum, take snapshots of a system just before and after an event. By comparing these two snapshots, we can learn a lot. From our earlier discussion of change of momentum and impulse, we have initial momentum plus impulse equals final momentum. When a net external force acts on an object, it imparts an impulse, J, to the object, changing its momentum. This is the same for a system of objects. If there is no external force on the system, the momentum of the system is conserved. A Newton's cradle demonstrates conservation of momentum. When the ball on the left is moving, the system momentum is equal to the momentum of the ball. After it strikes, it comes to a stop, and the ball to the right moves with the same momentum. The forces of the ball striking and being struck are internal to the system, so there is no external force and no impulse. Momentum is conserved. Conservation of momentum is a useful tool that can analyze the interaction of objects when the forces between the objects are much greater than any external forces acting on them. The internal structure of the objects, such as size, shape, and configuration, is not considered. The objects are treated as point masses, and their motion is described by their displacement, velocity, and acceleration. The analysis uses the object model, which is described by the above criteria. Objects in a closed system can interact with each other in two basic ways. They can collide, or if they are stuck together, they can explode, which means they just push apart from each other. In a closed system, both momentum and total energy are conserved, but the energy can change from one form to another. Conservation of momentum and change in kinetic energy predict what will happen in these events. Collisions and explosions are classified by the way the energy changes or does not change form. Inelastic collisions. Two objects collide, converting some kinetic energy into other forms of energy, such as potential energy, heat, or sound. The total kinetic energy of the system decreases. Elastic collisions. Two objects collide and bounce off each other while conserving kinetic energy. Energy is not transformed into any other type. And finally, explosions. An object or objects breaks apart because potential energy stored in one or more of the objects is transformed into kinetic energy. The total kinetic energy of the system increases. There are two types of inelastic collisions. In both cases, non-conservative forces, like friction, transform the system kinetic energy into other forms of energy, such as thermal energy. There are perfect inelastic collisions. Two objects collide, stick together, and move as one mass with the same velocity. General inelastic collisions. Two objects collide and bounce off each other. Their final velocities may be different depending on their masses and initial velocities. In an elastic collision, the initial kinetic energy of the system is equal to the final kinetic energy. The kinetic energy of each of the objects can change, but the system kinetic energy does not. There's really no such thing as an elastic collision. During all collisions, some kinetic energy is always transformed into other forms of energy. But some collisions transform so little energy away from kinetic energy that they are dealt with as elastic collisions. In chemistry, the collisions between molecules and atoms are modeled as elastic collisions to derive the ideal gas law. Other examples include a steel ball bearing dropped on a steel plate, a rubber super ball bouncing on the ground, and billiard balls bouncing off each other. A firecracker is an example of an explosion. The chemical potential energy inside the firecracker is transformed into kinetic energy, light, and sound. A cart with a compressed spring is a good example. When the spring is against a wall and it is released, the cart starts moving, converting elastic potential energy into kinetic energy and sound. Think for a moment. Can you see a resemblance between this phenomenon and either an elastic or inelastic collision? In both an inelastic collision and an explosion, energy changes between kinetic and potential energy, but they are time reversed. An inelastic collision transforms kinetic energy into other forms of energy, such as potential energy. An explosion changes potential energy into kinetic energy. Thus, the equations to predict their motion will be reversed. This table summarizes our collisions and explosion. We have the event in this column, the description of it, is momentum conserved and is kinetic energy conserved. In all of them, momentum is conserved, assuming that they're a closed system. So general inelastic objects bounce off each other. Kinetic energy is converted to other forms of energy. Same with the perfect inelastic collision, except in this case the objects stick together. Then elastic collision, objects bounce off each other, momentum is conserved, and so is kinetic energy. For an explosion, the object or objects break apart, momentum is conserved, but kinetic energy is not conserved.